You looking for a pencil?
And we're live from the fabulous room 1065. It's the Kelvin Dueck Show of Science.
That's actually pretty good.
Oh, we'll give it to him.
Just off the top.
Okay. You need an extra one, or you have an extra one? Hannah didn't get one? Hannah, come here. Get up.
Did you pause it or?
It's live.
We're live, people.
I'll be redoing all these next year and taking down my year one original lessons anyways.
No, those have to stay up.
Sadly, Dane, you won't be immortal. Basically, over the next few days, this is, in theory, how the planet should be working, and sadly, how as human beings, we're really screwing up the planet. Not the end of the world, though. Also, as human beings, how we can prevent or minimize or avoid screwing up the planet. We're looking at what are called nutrient cycles. What are nutrients? Well, nutrients are chemicals, that's what goes in the blank here, that are required for the life processes of plants and animals. Emily, there are a bunch of nutrients. And in fact, the word nutrition comes from the same word. We're going to be focusing on three of the main ones. And we're going to be talking about how they come from the earth, enter the life cycle, the biome, the biosphere, go back into the earth, and yes, once again, it's a great circle of life, Simba, a great circle of life. So all nutrients are constantly cycled through living things, us, plants, animals, life, bugs, fungi. And when they're out of living things, they end up in what we call stores. Not where you buy things, but like storage. Stores are accumulations of nutrients. And some nutrients get stored in the atmosphere, nitrogen, the ocean, or land masses. Without human interference, movement into the stores and back out of the stores is in balance. Sadly, with human interference, not so much. Two words. Here's your definition. So what we're going to talk about is the nutrient cycle. That's the continuous flow of nutrients into and back out of stores. Here is a picture, ideally, of a healthy nutrient cycle. It looks very overwhelming. Don't freak out. Here's how it's supposed to work. We're supposed to be, yellow is, and this is why, this is color, you guys got black and white, sorry. Yellow areas are meant to be nutrient stores, so some nutrients are stored in the ocean, the atmosphere, land. A lot of it is stored in marine sediments and sedimentary rock. Then we have cycles. So here is a cycle where for some particular nutrient, I haven't told you which one yet, there's consumers that plants or fungi or animals eat ingest the nutrient, then they decompose. There's bacteria that decompose them. The nutrient returns back to the store. Oh, but there's other animals, other things that produce the nutrients. Same here. And the big challenge is some of it ends up in very, very deep stores. Takes millions of years. Psst. Psst. Oh, thank you. What do we do? I'll turn the page. Kenzie, we disrupt the balance. How? Well, when we clear land, a lot of nutrients are stored in trees. We clear the land off, or a lot of the nutrient may have been stored in the soil, but when we clear the land off, now there's more runoff, and now that soil gets washed down into the ocean. Agriculture, urban expansion, mining. And the problem is, you may see here it says very slow, takes millions of years for this part of the cycle to occur. Does it take us millions of years to strip mine an area? No, we do it in a couple years. So we take from the very deep stores, it's very rapid, it takes tens or hundreds or less now of years. There are 5, count them, 5 chemical elements, also known as chemical nutrients, that limit the amount and types of possible life in an ecosystem. There are more than 5. These are the big 5. The first one, this is good review, has the chemical symbol C. The second one has the chemical symbol H. Hydrogen. The third one has a chemical symbol O, although technically O2, because it's a diatomic molecule. Remember Hofbrinkel? Hey, this is a good review. Oxygen. So already you say we need oxygen to breathe, yes. And what do oxygen and hydrogen, when they combine, form? Water. Do we need water to live as well? Okay. The fourth one, N2. Nitrogen. And the fifth one, a lot of kids are surprised. Phosphorus. Is phosphorus capital P? Yeah? Phosphorus. The first 4, CHON, the whole thing is CHON, but the first 4, CHON, C-H-O-N, those are cycled between living organisms and the atmosphere. Carbon, hydrogen. How does carbon get into the atmosphere? It combines with oxygen to form carbon dioxide. Carbon, hydrogen, oxygen, and nitrogen, those are cycled through the atmosphere. That's the main store. Phosphorus atoms enter our environment from sedimentary rock, the deep earth. But every one of these is essential to many of the chemical reactions that go on in your body. And it's a very delicate balance. Thank you for turning the page. Although there are 5 nutrients, we're going to be looking at 3 cycles. We're going to be looking at the carbon cycle, the nitrogen cycle, and the phosphorus cycle. The carbon cycle. All living things are based on carbon. What's so special about carbon? Well, if you think back to your Science 9, look where it is on the periodic table and think about Bohr diagrams. Carbon has 4 valence electrons, which means it can either accept 4 valence electrons and form bonds of 4 things, or it can get rid of them. It bonds very, very well. In fact, I think I mentioned this the other day, Brady, if you take the number of molecules that carbon is part of and you add up the total, it is more than all the other elements combining with their molecules put together. On the periodic table back there, what's right below carbon? Justice, can you see? Silicone has some of the same chemical properties. It's why scientists, when they're looking, whoever's doing that can stop. It's when scientists are looking for alien life, they think maybe silicone-based life might be possible. The problem, silicone is heavier, and so silicone blood would be so thick, we're not so sure that that would work all that well. There's issues. But if you ever watch any like Star Trek or anything, the classic, Mr. Spock has silicone-based blood, if you watch Star Trek, is their theory. How is carbon stored? Well, first of all, there are short-term stores. So it stays there for a bit, then re-enters the environment, stays there for a bit, re-enters the environment. 2 big ones, plants and animals. We are carbon-based life, us, animals, plants. When we decay into carbon. Or when plants or animals burn, charcoal, carbon. It's also stored in the atmosphere. I gave you a hint earlier. How is carbon stored in the atmosphere as a gas? Carbon dioxide, which is CO2. That's partly a problem with the greenhouse gases in effect. Long-term stores. Coal, It's carbon. Oil. Gas deposits. A lot of carbon is stored in those. Is it staying in those? Are we just leaving all the coal, oil, and gas alone, never touching it? No. It's also stored in sedimentary rocks, a process called, here's your new word for the day, sedimentation. So here's how it works. Emily, you're going to die someday. We all are. Let's suppose someday your body dies. Okay? As your body decays, it turns into carbon. Now, if you are an animal and you die out in the wilderness somewhere, probably some soil comes over you, or you get washed to the bottom of a lake. And then more soil comes over you, or you get washed to the bottom of a lake, or more soil, and eventually you have enough soil on top of you that it compresses you into a rock, sedimentary rock. So soil particles and decaying organic matter accumulate in layers on the ground or at the bottom of large bodies of water. And as more and more layers accumulate and more pressure builds up, over time, these layers are turned into rock. Most of what you see on the beach when you walk on the beach, a lot of that rock is used to be shells. Used to be marine life. Coral. So many marine sediments form from shells of marine animals, and they contain, let me get it right. Well, here's what they contain. What's Ca? Calcium. Does anybody remember what CO3 was? Calcium carbonate. That's one of the ones that's on your periodic table sheet on the back. That was one of those polyatomic ions. Pardon me? You pay big money for that when you go to the drugstore? There you go. So, carbonate, which is CO3 2 negative, it's got an ionic charge of -2. It's a combination of, well, what two elements do you see in there? Carbon and oxygen dissolved in ocean water. Add calcium, limestone, really is what we're talking about. So here are the estimated major stores of carbon on the Earth. Oil and gas, this is in gigatons. We figure there's about 300 or so gigatons. Where is most of it stored? Yeah, the first one, marine sediments and sedimentary rock. Lots of it. Oceans, coal deposits, soil, atmosphere, and so on. So, how is carbon cycled? Several ways. Photosynthesis, cellular respiration, decomposition. We'll talk about most of these. Oceanic processes, blank eruptions. What word do you think goes in front of the word eruptions? Volcanic eruptions. And forest fires. The first one, the source of all life on our planet, is photosynthesis. So what happens there? Photosynthesis is a chemical reaction that converts solar energy into chemical energy. Carbon, in the form of, what's CO2? carbon dioxide in the atmosphere. Plants need carbon dioxide. They take in carbon dioxide. Enters through the leaves of plants. That's why plants have leaves. It reacts with water in the presence of sunlight, and the bond between the carbon and the oxygen in the carbon dioxide molecule is split. And we end up with carbohydrates. What does the carbo part stand for in that word? Which element? Carbon. What do you think the hydrate part stands for? Where does that come from? What do you need to do to plants to keep them alive? Water. So this is why plants need water. Carbon dioxide from the air, water from the atmosphere, or if they're in your house, from you. In fact, as an equation, sun plus carbon dioxide plus water gives you sugar and oxygen. Energy plus 6 carbon dioxides and 6 water molecules gives you C6H12O6. There's a type of sugar. And you have 6 oxygens left over. Oh yeah, plants give off oxygen for us to breathe. That's why people put plants indoors. It freshens the air. So photosynthesis. The second way is what we call cellular respiration. This is us. When plants or animals need energy, we convert carbohydrates, sugar, and oxygen into, what do we breathe out? Carbon dioxide. What else do we breathe out? You'll notice it if you blow on a window on a cold day. Condensation, which is what? What liquid would that be, oh pray tell? Water. It's exactly the reverse chemical reaction of what the plants do. Plants combine carbon dioxide and water into sugars. Animals ingest those sugars, break them back down. We give off carbon dioxide and water. But when those bonds break, we get some of the energy that's part of the energy of life. Oh, when you eat more sugar, do you feel more energetic? Now you know. In fact, you'll see it's the reverse equation of synthesis. As a picture, 6 oxygen plus sugar. Oh, do we also need oxygen to live?
Yeah.
Now you know why. It's all for that chemical reaction. As a picture, there's your cycle. Photosynthesis, plants produce oxygen. Respiration, animals use oxygen. Animals produce carbon dioxide. Plants use carbon dioxide, turn it back into carbon and oxygen, sugars and oxygen. And away it goes. So, photosynthesis, cellular respiration, decomposition, also in all of our futures. You're really on a death kick lately, Mr. Dueck. It's the great circle of life, symbol of the great circle of life. What's decomposition? It's the breaking down of dead organic matter. When things die, what causes them to decompose? Well, the main ones are bacteria and fungi, the plural of fungus, fungi. And they convert organic molecules back into CO2, which is released into the atmosphere. This is the carbon cycle, and this is what you have also in the handout that I gave you. There's a lovely color one in your textbook, but I think the one you get on the provincial is black and white. It looks very overwhelming, but you want to focus, Kenzie, on just key areas. For example, let's look right here. Here is a sea surface gas exchange. It's intaking 92 what? I think we're in gigatons, it says in the bottom left. And it's releasing 90 gigatons. Oh, that's a net removal of 2 gigatons. You take in 92, you give back 90. 2 gigatons are removed from the atmosphere through sea surface gas exchange. And you can see they're nearly in balance. Plant growth and decay, you can see it's almost exactly in balance. 61 gigatons in, 60 gigatons out. Here's decomposition down here. You know what, Mr. Dueck, make the eraser and then they can see it. Here's decomposition down here. So we have carbon stores. Those are the ones that are in a rectangle. So 1,600 gigatons is stored in organic matter in the soil. 750 gigatons is stored as carbon dioxide in the atmosphere. Lots of it is stored in marine sediments and sedimentary rock. There's your oil and gas. In fact, that table that I gave you earlier, that's all built into here. Which ones are not very in balance? Hello? Putting out far more than we're taking in, than we're removing. Hello? Adding, and adding, not removing any. Okay? There's carbon dioxide from volcanic eruptions. There's photosynthesis, cellular respiration. So you do not need to memorize all of this. But Joe, you've got to be able to find stuff on this chart. And it is an overwhelming chart. But the message I have, Ty, is go hunting. It's there somewhere. It's there somewhere. So the homework that you'll be having later on will be using this chart quite a bit. What's our impact on the carbon cycle? Industries? Motorized vehicles. Clearing off the land. Fewer trees, that's carbon stored there. Agriculture and urban expansion. Our current data says that levels of carbon have increased by 30%. And there is, Amy, I want to be careful, there is still some guesswork on this. There is some data that suggests otherwise. Most of the best data seems to suggest that carbon has gone up and carbon dioxide is a greenhouse gas. Basically, Jessica, we are putting more carbon dioxide into the atmosphere than is coming out. Right there is your imbalance. Right there is your imbalance. Now, you may say, Leah, 5.5, I mean, you've got 38,000, you got 68 million, you got really big numbers here. That 5.5 doesn't seem too bad. That's where we're not sure. Leah, we don't know how sensitive our ecosystem is. We suspect, we don't know. I'm of the whole better safe than sorry philosophy. So, why do we care? Increased carbon dioxide is one of the leading contributors to climate change. Yep, us again. That's the carbon cycle. Josh, I said we were going to do 3. We're on track, we're on pace. Carbon cycle. Second one is the nitrogen cycle. Nitrogen is an important concept or component in your... What's DNA? It's really the molecule of life. Okay. It's also important for plant growth and animals, humans included. It's important for muscle function. It's important in the formation of proteins, which is this stuff. Okay. How is nitrogen stored? The major store of nitrogen is the atmosphere. Most of our atmosphere is nitrogen. Only some of it is oxygen and other trace elements. The reference that I gave you, turn the page past the carbon cycle. At the back of the carbon cycle should be the nitrogen cycle. Like this. This one on the provincial you'll get in color. I don't think the color is absolutely necessary for you to be able to translate it, Jessica. I think it just makes it look pretty. So I said, find N2 in the atmosphere. Right up there. Right at the top. Atmosphere is primarily nitrogen with some traces of other stuff as well, but lots of nitrogen. So keep that chart handy, folks, if you don't mind. It's also stored in organic matter in the soil. So we have ammonium, which is NH4+. And we have nitrate and nitrite. You don't need to memorize those. Those were part of the polyatomic ions that I gave you back on our very first reference sheet. It was the periodic table sheet that I gave you. Nitrate and nitrite. I spelled trait the same way. I saw Miller pointing and going, say what? Nitrate and nitrite. Yeah. I never make mistakes. So how is nitrogen cycled? Where is most nitrogen? In the atmosphere as N2. Problem is, most living things can't use that. So most of the nitrogen cycle is involved in converting nitrogen from the atmosphere, Curtis, into some kind of a form that plants and living things and us can ingest. So converting it into a form usable by plants, and then when we eat them, eventually animals. By the way, anybody here live on a farm that grows a crop? Because if you do, you'll recognize this is fertilizers. The whole fertilizer industry is all about finding ways to take nitrogen from the air and put it into a form that plants can use. How? Well, nitrogen fixation is the process in which nitrogen gas, the air gas, is converted into compounds that contain nitrate, come on T, NO3 negative, or ammonium. Those are the two main fertilizers, ammonium, both of which are usable by plants. So if you turn the page, I wrote here, find NH4 on your copy of the table. Let me get the copy of the table in a secondary document. That'll be better, Mr. Dueck. Science 10 data booklet. Come on, computer. You can do it. Can you see NH4 on the table?
Yeah.
Yes? Okay. The nitrogen cycle. And I think I can go fit width. Perfect. So NH4, fertilizer application, it's there, nitrogen fixation. So nitrogen fixing soil bacteria can help convert stuff into NH4, and we also do it in factories. So how does nitrogen fixation occur? It occurs through, this is a cool one, lightning in the atmosphere. That's enough energy. Is that a hand up?
Yeah.
Quickly, buddy. It occurs through certain bacteria. There are some bacteria that have a mutualistic, what did mutualistic mean? Both parties benefit. Relationship with legumes, beans, and some trees. The plants get ammonium, and the bacteria get sugars from the plants. The bacteria convert the nitrogen into a form that the plants can ingest, and then the bacteria also feed off the roots of the plants. It occurs through what we call cyanobacteria that live in water. And it occurs through the decomposition of dead plants and animals or waste by nitrogen-fixing bacteria. This is why composting makes good fertilizer. What you're really saying is, I want that chemical reaction to occur, let the bacteria do their thing. Now it's a nitrogen-rich soil in a form of nitrogen that plants like. Go spread it, plants will grow. So that's called nitrogen fixation. And we have another word, unfortunately very similar, nitrification. Some plants are picky. They can't use NH4 ammonium. They specifically need nitrite or nitrate. And this step is done for them by nitrifying bacteria. Now the plants can use it, and nitrate and nitrite are taken up by the plants through their roots, used to make plant proteins, etc., and then animals then eat. I wrote here, find these on your table. Again, do you need to memorize all of this? You need to be able to find it on the table and understand what the heck is going on. So let's find some nitrifying bacteria. Oh, the yellow in the bottom here on my color table. And where does it end up? Some of it ends up being denitrified back into the atmosphere, and this one says, plants eat it up as well. You kind of figuring out how you can follow? It's a big chart with lots of data, but if you kind of concentrate, you can, I hope, follow through what's going on. So the message I have is, if you see a nitrogen question, you're saying, go look at the nitrogen cycle. If you see a carbon question and you're going, say what? Go look at the carbon cycle. Okay, so there's another example. How is nitrogen removed from ecosystems? I know this is a long lesson. Bear with me, folks. Well, first of all, the opposite of nitrification would be denitrification. Denitrification. There are some bacteria that instead of converting atmospheric nitrogen into a form that plants like, they take the form that plants like and they convert it back into atmospheric nitrogen, into N2. It's also returned through volcanic ash as ammonia. That's why, as human beings, so many civilizations live close to volcanoes. It's not because they're stupid, it's because it's really good agriculture there. And also leached from the soil into groundwater and streams. So can you find denitrification steps on your table? Let's see. Denitrification, on mine it's in pink. You can see here's some denitrifying bacteria right here. And it ends up going eventually back up into the atmosphere, and then, if it gets hit by lightning, it may be, you may have atmospheric fixation, sedimentation, all sorts of different cycles going on here. And again, Brad, what I'm trying hard to convey to you is, if you're not sure on the test or on the provincial or in the homework, say what, go find it somewhere on the chart. Jessica, if that was it, it would be lovely. And then there's us. How do we botch this up? Well, first of all, we add it to the atmosphere in the form of, let's review. How many nitrogens in this covalent bond? What's the subscript right there? It's invisible. Right there, it's invisible. 1. How many oxygens? We would label that, this is good review, nitrogen monoxide. Remember. What do you think we would call the next one with 1 nitrogen and 2 oxygens? Do you remember the plural, the prefix for 2? Or nitrogen. Oh, what great review before the provincial exam. I'm going to be trying to fit some stuff, and I'm also going to say, Emily, do you have a science teacher who's like maybe put all his lessons online as videos or something like that you could maybe watch some of the topics that you're a little shaky on? I am trying, this is where I apologize, I've let you down. Next year I will have a complete set of 1-hour reviews for each unit as videos. It's not going to happen this year. Sorry.
Are we having a test for this?
Pardon me?
Are we having a test for this?
I hope so. I don't know yet. I'm going to be figuring that all out this weekend. Let's keep going. Also, we add nitrogen through the burning of fossil fuels and the treatment of sewage. It forms acid rain, which is nitric acid. We've gotten a little better on that. In the 70s, acid rain was really killing a lot of lakes in northern Canada. We're a little better, but... So, what happens? We add nitrogen to the soil for plants. Fertilizer. Do the plants use up all of the fertilizer? Does every bit of the fertilizer that we add go into the plants? No. What else do we add to crops? What else do plants need? What liquid, Darian? Okay, we dump water on them, or the rain goes. That ammonia, that nitrogen, that fertilizer that the plants didn't use, it runs off, and it runs off into lakes. Well, what happens once you have nitrogen-rich lakes is algae grow up fast. They use up lots of oxygen, they block sunlight. The aquatic plants begin to die because those plants underwater need to be able to pull oxygen and carbon dioxide from the water. Oh, the dead matter provides food for microbes, increases the competition for oxygen, the water becomes deoxygenated, fish die. I don't know if you guys can see this photo in color. This was the original lake. There's a huge algae bloom. The entire lake has gone green. Nothing can live in it anymore but the algae. There are huge algae blooms out on the ocean right now. So, chemical leaching from soil causes, new word, eutrophication. What's that? Increased nutrients result in increased plant production, but those plants then die and rot, and now you're getting more decay. It's not in balance. Algae blooms deprive other plants and animals of sunlight and oxygen. You may notice we're nearly done. We are. I apologize that it took this long. Well, it's a short class today. So we have the carbon cycle, yes, and a chart for that. We have the nitrogen cycle, yes, and a lovely chart for that. Hey, we have the phosphorus cycle. Hey, turn your chart to the next, but there's a lovely chart for that too. These are the 3 charts that you'll get on your test for this unit. These are what you'll get on the provincial exam, except the provincial exam ones are color. Phosphorus. Phosphorus helps to carry energy to plant cells and animal cells. So it's essential to root development in plants, and for human beings, we use it in our bones. So how is phosphorus stored? Carbon, we said, and nitrogen, those are stored in oceans and in the atmosphere. Okay. Phosphorus is actually stored in rock. It's stored in a chemical called, a compound called phosphate. So there is no atmospheric store. Phosphorus comes from rocks. So how do the rocks end up in the system? Well, the first one takes a long time. It's basic weathering of rocks. Rain, wind breaks bigger rocks up into smaller rocks. Chemicals break bigger rocks up into smaller rocks, which then break up into smaller rocks, which then break up into smaller rocks, etc., etc., etc. So the chemical processes, acid rain, and then there's something called lichen, which is a life form that breaks rocks up. Physical processes of weathering, we have wind, rain, and also the freezing and thawing cycles. When water freezes, it expands. So if water gets into the cracks of rocks as liquid and then it freezes, it expands, making the cracks a little bit bigger. Then it melts, then more water gets in, it expands, making the cracks a little bit bigger. We also have uptake from the soil by plants. Plants break up rocks. Trees break up rocks. You may have noticed that if you've ever seen a plant growing up out of a cement driveway or something like that. There's often a crack associated with it. Animals eat the plants, and then when they decay, that gets into the system as well. Then we have geologic uplift. Plate tectonics, mountain building stuff. So I wrote here, look at your table in the phosphorus cycle. Find these let's go find the phosphorus cycle. Here, phosphorus. Hey, the phosphorus cycle. Again, here's our key. The circular numbers represent flows in millions of metric tons. The square rectangular numbers represent stored amounts in millions of metric tons. So you can see much of it is stored in the Earth's crust. 20 billion tons. 100 million tons is stored in Earth sediments. Some of it is mineable, and you can see all the different options. Geologic, let me get it there, that's what I want, the hand. Geologic uplift, phosphate rocks, weathering, it eventually ends up in plants. Animals eat the plants, decompose, it ends up back in here. Marine life has some of it is stored in marine life. What's guano? Bird poop. Okay. You can call that to somebody as an insult. So, human activities. It's used in fertilizers. Holy smokes, we're going to finish the lesson. It's used in detergents. Where do fertilizers end up when we add water to them? In the ground. Where do detergents eventually end up when the washing machine drains? In the ground. It's mined from rock and bird guano. There are complete countries and islands where they do nothing but mine this stuff because it's good fertilizer. Can't see. Psst. Thank you. Extra phosphorus is added by runoff from farms, untreated sewage, and large-scale livestock farming. It can cause fish kills. Reduced phosphorus can be caused by a change in plant life in an area, and it can reduce algae, which then affects the whole food chain. So these are the 3 cycles. What's your homework? Officially, this is not going to be due first thing Monday. I'm going to give it to you now. We are going to be doing another lesson on Monday, but I'll hopefully be able to give you more time in class on Monday to practice some of this. So here is your homework, my children.